In this module, we are going to be talking about another method that has been introduced way back in the early 70s called nudging. I am going to provide the basic principles of nudging and some of the associated questions relating to the design of nudging schemes. So, what is nudging? The model is always used to create a forecast. The goal of data assimilation is to make the model to fit the observations. So, this fitting was done by looking at the sum of the square differences between the model predicted variable and the observation to decide on the values of the optimal values of the parameters and the initial condition from which we started the model forward, and that is one of the themes that underlie 4D VAR data assimilation or forward sensitivity based data assimilation. Nudging is an alternative method. In nudging, what do? You compute the forecast error, which is the difference between the model predicted observation and the actual observation. This error in the forecast is often used as a forcing, the forcing that makes the model move towards the observation. This ability to force the model by adding a force that depends on the forecast error is the fundamental idea behind the nudging scheme. So, to nudge, to be able to force, to be able to coerce the model towards the observation. These words force, nudge, coerce essentially captures the fundamental principle that underlie this notion of nudging algorithms or nudging methods. A bit about early history. Anthus in 1974 introduced the nudging method. He used this for initialization of hurricane prediction model. It was published in Journal of Atmospheric Sciences in 1974. Hawk and Anthus in 1976 further explored the use of nudging schemes, again within the context of hurricane forecast, and their joint paper was published in 1976 in Monthly Weather Review. The idea is to use the model forecast error to force the model so as to reduce the forecast error. So, it is a kind of a feedback principle. So, the model makes a forecast, observations are there is a forecast error. I am using the forecast error to be able to force the model to be able to reduce the forecast error. This is the fundamental principles that underlie any feedback control mechanism. So, it is a kind of a feedback control theory that is brought to focus by this nudging scheme within the context of data assimilation methodologies. So, to get a feel for this nudging scheme, let us consider a state xk, a time k which is an Rn, m is a map from Rn to Rn. The forecast model I am assuming to be deterministic with x0 as the initial condition. The observations are again nonlinear function of the state, x bar be the true state of the system that is not known. I only have information about the true state through the observation. Vk's are the observation noise, h is the forward operator. Again, I would like to emphasize the notion of a true state, and the observation noise is Gaussian, is a standard setup. So, what is the difference between this and the Kalman filtering scheme? The model is deterministic. So, this has commonality with 4D VAR. In the early 70s within the meteorological literature, they considered the model to be perfect. So under the perfect model assumption, noisy observation, they would like to be able to use the forecast error to force the model, which will in turn make the model move towards the observation. So let M bar be the true model dynamics. So I am going to now develop a general theory. Let M bar be the true model dynamics. X k plus 1 bar is equal to M bar x k bar with x naught bar as the initial condition be the true unknown deterministic system being modeled. If M bar is equal to M, the model is perfect. If M bar is different from M, the model has an error. So I am now going to consider a generalization of the nudging scheme where I am going to think that the model may or may not be perfect. So let M bar x be the model error. M tilde x is equal to mx minus M bar x, that is the model error. X tilde 0 is equal to x of 0 minus x bar 0 is the error in the initial condition. So if I use M as the model to be able to generate the forecast xk, xk is the forecast generated out of the model M. M may have errors. Zk is the observation coming from measurements of the real world. So Ek is the forecast error as given in 4. Now what is the nudging scheme? Consider an otherwise deterministic model. Xk plus 1 is equal to M of xk. Please understand, xk is the forecast starting from x naught on the model M. M may have errors, the initial conditions may have errors. So the forecast xk generated out of the model equation may have errors. I would like to be able to add a forcing term. Please remember, Ek is the forecast error, G is the matrix. So G times Ek is the forcing that is artificially added to the model. The forcing always makes the solution move towards a particular goal. Our aim is to be able to find G such that asymptotically the model state moves towards the observation, which represents the true state of the model. So G is called a gain matrix. G is called the gain matrix. G is again an n by m matrix. G of Ek is a vector. There is an artificial forcing applied to the forecast model. The error term Ek represents a state feedback. Y, please remember, Ek is equal to Zk minus h of xk. Therefore, I am using the state information to force the model. So that is what is called the state feedback. The idea of the state feedback has been around since the early days of steam engines. The gain matrix G in the early days was empirically designed. I am now talking about some of the early approaches to design of nudging scheme. The early approaches period from 1974 to 1990. During this period, several people have applied nudging schemes to be able to make data simulation schemes. In other words, you are trying to use the data to force the model, or the forecast error which involves data to force the model. So the model response to external forcing depends on the intrinsic relaxation times of the model. So what is the basic idea? Gek is the forcing. Gek is the forcing to the model. If you apply a force to a dynamic model, how long does it take for the model to respond to the initial force? That depends on what is called the relaxation times, the intrinsic relaxation times. In engineering, we also call it time constants. So the design of G in the early days was essentially based on the time scale considerations. What is the intrinsic time scale of the processes involved? How long does it take for the model to respond to the external force? So the value of the matrix G was essentially heuristically decided, and the considerations was essentially based on the time scales of the processes involved in the model solution. So the nudging scheme in phi has a strong similarity to the design of observers, the theory of the design of observers in control theory. The theory of observers was developed earlier by Leuenberger in 1964. It is not very clear whether Anthus and his group knew about this work on Leuenberger's work on observers, but the observer based design as well as the nudging schemes had a very strong similarity structurally. So now you can see Kalman filters came from control theory. The notion of observers was already in existence in the early 60s in control theory, and maybe it was invented independently by Anthus, but I would like to emphasize a very strong similarity between the nudging scheme as used in geophysical literature as well as the observer designs in control theory. So you can see there is a great influence of control theory in the design of data simulation algorithms. So now I am going to talk about the post 1990 era. What is the question? How to so before 90, people were heuristically designing values of the gain matrix G to be able to force the model towards the model state towards the observation so as to reduce the error. The only consideration they used was based on relaxation time, and that is all. But in many cases it worked very well. But as the theory of 4D war was well developed, as the theory of optimal methodology was very well understood, the notion of being able to estimate the optimal state and the theory behind the strong constraint formulation, weak constraint formulation was well understood. Around the turn of 1990, the emphasis shifted towards trying to objectively design the gain matrix that essentially dictates the amount of forcing that was applied to the model equations. So two approaches emerged within this quest for optimal approach to the design of the gain matrix. One is the 4D war-like methods. Another is the two-stage Kalman filter-like methods. The 4D war methods sprung up in the early 1990 to 1994. The two-stage Kalman-like method arose around was announced around 2003. These methods developed algorithms for optimal estimation for G. So what did they do? Well, G is the known, and they wanted to be able to optimally estimate the appropriate value of G. So they brought the full force of least square based estimation theory within the framework of 4D war, or within the framework of two-stage Kalman like methods. Even though these theories were known, in 2011 it was pointed out there are the claims of optimality that were obtained by these researchers were found to be a little defective. It turns out the optimal estimation of G is more subtle and involved than it appears on the surface when you read the papers on 4D war-like methods as well as two-stage Kalman-like methods. We are going to talk about both the methods as well as some of the problems associated with the methods and ways to go around some of these challenges. So 4D war based methods. Stauffer and Seaman, Stauffer and Bao, Zhao, Nawan and Lidemey were some of the earliest people who were working in trying to find the optimal value of G. So referring to the equation 4, let me go back. Equation 4 at the bottom of slide 4 is the forecast error of the nonlinear model. So 4D based methods were introduced by at least 3 sets of authors: Stauffer of Seaman, Stauffer and Bao, Zhao, Nawan and Lidemey in the early 90s. Referring to 4, which refers to the expression for the forecast error, let E1, E2 to En be the set of forecast errors created by the model forecast or based on the model forecast. So in other words, you can see like the 4D like scheme here. So while the original nudging scheme involves essentially adding a forcing to the model and let the model evolve, these people coming from the 4D methodology, their aim is to be able to design the optimal G. So they are doing an offline experiment. What is the goal of this offline experiment? Let us pretend that there are n observations. If there are n observations, then there are n forecast errors. If there are n forecast errors, then I can compute the least square cost function J2 of G, which is given by Ek, Rk inverse the transpose, I'm sorry, the inner product of Ek with Rk inverse Ek. What is this? This is the weighted sum of squared errors. Please understand, this is exactly the cost function that was used to minimize to find the optimal initial conditions and parameters in 4D as well as forward sensitivity based method. You can see the approach, because 4D is something they know very well, and they were part of the development of the 4D techniques. So they would like to look at this scheme as though it were a 4D scheme to be able to estimate G. Another difference is that in the classical 4D they used these kinds of objective function to decide the optimal initial condition. In the nudging, I am not going to worry about where the model starts. Initially the model may have forecast errors, but as time goes on, adding GEK forcing to the model will try to correct the model forecast errors while the model is in evolution. So that is the basic idea. In the 4D we wanted to be able to start from the initial optimal initial condition, so that starting from the initial condition the new forecast generated will match the observation as much as possible. Here that is not the goal. Initial condition could be anything. Our aim is to be able to simply move the model towards the observation as the model starts operating. So they were able to understand that I may not be able to correct some of the initial forecast errors, but in time the future errors may go to 0 or may become very small. That is the idea. So you can see in the 4D the J2 function was a function of, if you recall, we called it function of Jx0. That is in 4D. In here we are calling it J of G in nudging. So the independent variable with respect to which 4D was with respect to which the minimization was done is the initial condition. The independent variable with respect to which the minimization is going to be done in the optimal design of nudging matrices is G. The elements of the matrix themselves G. That is essentially the difference, but rest of it are very similar. So mathematics is not too different from what 4D involves. Again, they wanted to bring in the notion of background. Why this notion of a background is useful? Because in the pre-90 era they have been very successful in trying to demonstrate the usefulness of nudging scheme based on some empirical values of G. So that is a knowledge they knew worked reasonably well in many circumstances. So they don't want to throw that knowledge out of the window. So they would like to be able to use some of the prior knowledge where nudging had worked. So they would like to be able to give the benefit of doubt. So they said let G hat be the prior estimate of G obtained through empirical consideration relating to the relaxation times of the model. So quite a lot of time scale analysis of the models have been done. So they know which time scales respond to what type of forcing, and that knowledge they didn't want to go as a waste. So they assumed, well, we will also want to take advantage of some of the earlier estimates. So let G hat be a prior information. So you can see now they are combining a prior and the new information coming from the forecast errors. They would like to be able to combine the two types of objective functions. So the prior term gives rise to what is called a penalty term. A penalty term is as follows: J penalty of G is G minus G hat beta times beta over 2 is the square of the Frobenius norm. You may recall from our example from our module on matrices, the Frobenius norm square, I will simply say the Frobenius norm. So the Frobenius norm by definition is equal to sum of Aij square, sum is over Inj. It is something like the Euclidean norm. I simply take the sum of all squares of all the elements of the object. If it is a vector, there is one set of objects. If it is matrices, there is another sets of objects. So it is simply sums of squares and the square root of that. So that is called the Frobenius norm. So the penalty term relates to the difference between the two. So what does it mean? So what is the penalty term tells you? I am interested in designing an optimal G. I know they have been using G bar, but G bar, G hat. The G hat was obtained from heuristic consideration. I am trying to design G optimally. I am trying to design G optimally based on the forecast sums of forecast errors. At the same time, I don't want my G to be far removed from G bar because G bar has already worked. So I want to find an optimal G that is a compromise between minimizing the sums of forecast errors, at the same time going not too far away from G hat. So we have defined the Frobenius norm in here. So the constant B is called the penalty parameter. If the constant beta is large, since I am going to minimize, the product has to be small. So if beta is large, G will be much closer to G hat. If beta is small, I am trying to relax the distance between G and G hat. So by essentially picking the value of beta, one can have a variety of different range of G with respect to G hat. In other words, I have G hat here. Do I want my G to be in a sphere of radius dictated by the value of beta? So if beta is small, it will be, you have more freedom for G. If beta is very large, because if beta is large and the norm is large, it will not come to minimum. So if beta is large, the only way to minimize it is to force G towards G hat, so that G minus G hat will be much smaller. So that is the idea of the penalty term. So we have two terms now. One, I don't want my new estimate to be too far away from the old estimate that they have used based on heuristic consideration. I am giving myself some freedom by being able to choose the penalty term. At the same time, I have the forecast error term, sums of squared errors. Therefore, I am now going to conjure up a new criterion, which is Q1G, which is going to be a sum of J2 plus JP. Why I call it J2? Because it is a 2 norm, JP, P for penalty term. So compute the matrix G that minimizes Q1G, where the nudge dynamics is going to be used as a strong constraint. Please understand that the nudge dynamics is the one that is going to be ultimately used in the forecast. So then I cannot decide G or minimize this independently. I have to find an optimal G within the context of the dynamic models. Therefore, it is formulated as a strong constraint problem. Okay, so we have now essentially formulated the problem. So what is that we can do? We can essentially develop the first order adjoint method that was developed in 5.1. So we can use the first order adjoint method of module 5.1 to be able to decide on the optimal G. So what is that we do? We start with the G, run the model forward in time, compute the forecast errors, compute the objective function, and evaluate the gradient of the objective function. And then once you evaluate the gradient of the objective function numerically, I can use it in a gradient method so as to minimize the elements of so as to minimize the objective function Q and G. Recall that adjoint method gives rise to the gradient, which is then used in some minimization algorithm until convergence, and we have already talked about minimization algorithms in module 4.3. So because we have done a lot of things relating to adjoint methods, relating to optimization methods, our discussion becomes simpler because we don't want to repeat the entire derivation. An interested reader can simply apply the methods and derive the expression for the gradient. So this was the theme of people who wanted to be able to estimate G optimally using 4D war like method. But there are a couple of philosophical challenges. What is the first one? Getting the prior value of G hat may not be as simple as one deems with. Why is that? If you change the model, if you change the process for hurricane prediction, the dynamics is of one type where the time scales are of one type. If you change the model equation and go from hurricane to other physical processes, again the time scale analysis will be different. Therefore, the choice of G hat depends very much on the process that is to be used or the process that is captured by the model. So in general, there are no specific guidelines for choosing G hat. So the only thing that we can fall back on is that for those processes for which nudging method have applied in the early years, you have a reasonably well defined G hat, but in general there is no clear cut algorithm for generating G hat. So the difficulty with respect to getting the prior value is one problem. To appreciate the second difficulty, and this is a more serious problem, we want to be able to write phi using 2 as follows. So let us go back to phi and 2, what they are. So phi is the nudged dynamics, phi is the nudge dynamics, and 2 is the observation equation. So I am now going to combine the 2 to be able to come up with the exact equation for the nudge dynamics. So when I use 2 and phi, the explicit equation for the nudged model becomes this. Where is this coming from? Please understand, xk plus 1 is equal to m of xk plus g times ek, and ek is equal to zk minus zk minus hf xk, and zk is equal to h of x bar k plus vk. So these are all the various quantities that are involved in here. So zk is equal to h of x bar k plus vk. X bar k is the unknown true state. So I substitute zk in here, I get ek, I substitute ek in here. If you do these substitutions, the resulting equation takes this form. So now let us look at the structure of this. It consists of a deterministic component. Why this is deterministic component? M of xk is a deterministic model forecast. H of xk bar, the true state, that is the deterministic. H of xk, that is the forecasted observation, counterpart of the observation. So this term h of x bar k minus h of x k is the actual expression for the forecast error, true minus the actual. G is the multiplier constant. So this term is essentially a deterministic term. The vk term now occurs as gvk, so that is a random term. So nudging method in fact induces a stochastic dynamics, because observations are stochastic. Even though your model is deterministic, the process is stochastic because the observation always have observation noise. If you look at this carefully, you can readily see this is the first order nonlinear autoregressive process. So what does it mean? xk is not deterministic, xk is stochastic. So in the previous approach to 4D war, they did not realize that that is a stochastic term that is affecting the evolution. They simply assumed that there is no such thing as a stochastic part in the forcing. They applied the 4D war like scheme, and they found optimal within the framework what they had built. But a clear examination of that of those ideas essentially tells you a correct formulation has to take into account this autoregressive process. Why this is autoregressive? X depends on the xk plus 1 depends on the previous xk. So what is an autoregressive process? This is k plus 1, this is k. So k plus 1 depends on the previous values of the state. So I am dependent on myself at the previous time plus a random noise, So once you recognize this is an autoregressive process, xk becomes random. If xk is random, what does it mean? Xk, the trajectory is a random process. So this essentially tells you xk's are serially correlated, xk serially correlated. Why they are serially correlated? Let us go back now. I have x naught, I have x1. X1 has the effect of then x2, x3. x3 depends on x2, x2 depends on x1. x1 is random, x2 is random. Therefore, x1 and x2 are not totally independent. They are, x1 is a random process, R is a realization of a random process, x2 is a realization of a random process, x2 depends on x1. So there is a serial correlation that is induced. So this serial correlation was neglected in almost all of the treatment of nudging schemes, and this observation was first made by us. So we would like to be able to make amendments to the optimal estimation of G by taking this serial correlation into account. So that is one of the second problem. Not only second problem, but also we propose a solution to go around and solve this second problem. So let's talk about this now. So now that we have established that the errors are serially correlated, so what did I want? I would like to be able to define a matrix C. What is this matrix C? The matrix C is is RNM times RNM. Why NM? M is the size of the forecast error. Please understand, please recall, this is the size of the forecast error. I have N observations. So if I consider all the observations together, as well as I consider a gigantic vector, the set of all forecast errors from time 1 to n, I am sticking them all together to get a gigantic vector which is RNM. If I have a vector RNM, its covariance must be RNM times RNM. So C is represents a gigantic matrix that represents the serial correlation between all the states. So now we are going to define okay, now you may ask a question, how do you know C? We have to estimate C, because once we know that they are serially correlated, we have to take that correlation into account in trying to define your weight function, and that is what J3G is all about. So J3G is an alternative to J2G that we saw earlier. J2G neglects the serial correlation. Now this is a new objective function that involves the weighted sum of squared errors. The weighting is related to the serial correlation matrix. So now we can minimize, with respect to a new function. Instead of Q1 is Q2, Q2G is equal to J3G plus JPG. If you minimize G2G using the nudge dynamics as a strong constraint model, you try to take into account the serial correlation, but computing the covariance C in 12 is not easy. Hence, in principle, finding an optimal G for nonlinear model is a difficult problem. So in our view, the so called optimal methods that were proposed between 1990 and about 2005, covering a period of about 15 years, the claim that they are optimal is indeed are not optimal. So that is the critique about the methodology, and we are also going to suggest a way out of this critique. But in general, so what does it mean? Nudging you can implement heuristically. More often than not it works. But if you want to move away from heuristic methodology to an optimal methodology where I am trying to design a G which is best, then you have to take into account all the processes that are involved. If you look at it carefully, there is a serial correlation. Trying to minimize the errors without taking that serial correlation into account always leads to results that are not optimal. That's the simple way of looking at what's happening in here. So in order to be able to define the matrix C, I have to look at the structure of the forecast errors, because if you want to be able to understand the serial correlation, I need to understand the structure of the forecast errors. So let us spend a few minutes on trying to understand the structure of the forecast errors within the context of being able to consider the nudging scheme as the first order nonlinear autoregressive process. That is the next step. So let this be the true model. Let x naught bar be the true but unknown initial state. So what does it mean? If you use the true model and starting from the true initial state, the model forecast will be perfect. It will match the observation modulo noise. Please understand, when we say match only in the deterministic sense. We cannot match the random process anytime. So whenever we say something matches something, it is always modulo noise. Noise is something we may have to live with. So if I iterate this equation, xk bar is equal to m bar k to the power k x naught bar. So observation is given by this equation. So I can substitute 16 in here to get 17. So the expression for zk, the observation at time k, is given by equation 17. So x1 is equal to m of x naught. Sorry. So I am now going to talk about the nudged forecast model. In the previous case we talked about the unknown true forecast model. M may not be equal to m bar, that means there is a model error. So what is that I am now going to talk about? I would like to be able to simultaneously arrange G such that it not only corrects for the model error, also it corrects for the initial condition error. So I am trying to kill two birds in one stroke. So let x1 be equal to m of x naught be the initial condition. For any k greater than that, m of xk plus g times zk minus hk, that is the nudged model. The nudged model can be written like this because I am considering a linear model to be able to do things a little more precisely. For nonlinear, I would like to be able to expose the difficulty for the linear model. If the linear model is difficult, the nonlinear model at least is one notch more difficult than the linear model. That is the aim in here in this discussion. So my nudged model becomes 19, where the matrix A is equal to m minus gh. G is the gain to be determined, h is the forward operator, m is the one step transition matrix for the linear model. So I am assuming the model is linear, the observations are also linear function of the state. So iterating this equation 19, I get this, and zk contains the unknown truth plus noise. So the noise is embedded within the zk term. The noise is embedded within the zk term. I hope that is clear. So 20 is obtained by iterating 19. A simple iteration gives you the expression. So what is this expression? The nudged state at time k depends on the state at time x1 plus anything beyond. Substituting 17 in 20. So let us go back to, this is 20. What is 17? 17 is an expression for the observation based on the model's solution. You get an expression for xk, which is the model state, the forecast state, given by this expression. It's a funny looking expression, a little complex expression, but I don't think there should be any difficulty in trying to verify that. Why am I trying to find that? Because I would like to be able to pin down the forecast error. So zk minus h of xk is the forecast error. Now therefore I know zk, please remember zk is equal to h of xk bar plus vk. H of xk bar we have already computed in equation 16. Based on h of xk bar, I also have a relation for zk from 17. So I can substitute for zk from those equations in here. I have already computed xk in the previous slide. Let us look at it once more. That is equation 20. So substituting all these things, what do I get? I get an explicit expression for the forecast error in the nudged model. Why is that? If I want to be able to compute the forecast error covariance, the serial correlation, I need to be able to get an explicit expression for the forecast error itself. That is the first step, and that is what we have accomplished. So look at the structure of 22. 22 has several terms. This is the first term, this is the second term, this is the third term, this is the fourth term is the summation. The fourth term itself is a sum of two terms, but among all these Vk is a noise term, Vk minus 1 minus j is a noise term. So there are two noise terms, the rest of it are deterministic terms. So the error is noisy. You can also see the error at time k depends on Vk as well as the error I'm sorry, the noise at time Vk as well as the noise at time 0 to 0 to time k minus 2. So that means there is a serial dependency among all these noise expressions. So when j is, you can really see. So I'm depending on Vk. Then when j is 0, that depends on Vk minus 1. So let me write that down. When j is equal to 2, that depends on Vk minus 2. When j is equal to k minus 2, that depends on V1. So therefore Ek, the error dk, does not only depend on Vk but also the entire sequence in the past. It is this dependency of Ek on the entire noise sequence up to including time k that induces the serial correlation. I hope that part is clear to you. It is this serial correlation I am now going to have to extract. I am now going to rewrite this expression Ek for the sake of convenience, a deterministic part plus the random part. The deterministic part has this expression, the random part has this expression. So 24 and 25 correspond to the deterministic part of the forecast error and the random part of the forecast error. So you can see 23 is deterministic, eta k is stochastic. What is the stochastic part? Stochastic part is again the noise from the past, the noise from the present. The past noise are weighted by the powers of A, and you may remember A is equal to m minus gh. So what does it mean? The random part of the forecast error depends on the model dynamics, depends on the forward operator, it depends on the model dynamics A, it depends on the forward operator H, it depends on to be chosen the matrix G, which is the gain matrix to be used in nudging, and of course all of the errors in the observation starting from time 0 to this time, to the time k. Therefore the expected value of Ek is equal to the deterministic part. The expected value of eta k, the random part, is 0. Now I am going to further, if I assumed a general value of n, the expressions are gets more complex. So instead of n, I am going to assume n is equal to 3 to just get a feel for the expressions in this quick discussion. So let us assume I have 3 observations at time k is equal to 1, 2 and 3. And so by specializing this, now look at this now. The previous expressions, they go for k 1 to n. N is the last observation time. To simplify, to get that aha feeling, I am simply going to assume n is equal to 3 without loss of generality. So if I substitute n is equal to 3 and simplify, the expression the expression for the random part of the forecast error, which is eta that's this, that is that is that. Look at this now. Eta 1 depends on V1, eta 2 depends on V1 and V2, eta 3 depends on V1, V2, V3, eta 4 will depend on V1, V2, V3, V4. So this means etas are correlated. It is this correlation makes the 4D scheme little defective in the sense they have not taken the entire weight function that accounts for the serial correlation. A simple exercise in statistics, computation of correlation, tells you Cij, which is the correlation between errors at time I and errors at time j, is given by expected value of eta j transpose. In the case when n is equal to 3, eta 11 is given by r. What is r? R, so please go back now. Vk is equal to n of rk. It is generally assumed rk is identically equal to r. Why? Vk's are coming from instruments. When we buy instruments in bulk. So I am going to assume all the instruments that make measurements are the same type. That means the covariance of the error characters of the instruments are the same. So rk does not depend on k, rk simply is r. So that's a very useful assumption. Even though the theory I can continue with rk, I do not want to unnecessarily complicate the expressions by trying to be general. There is no loss of generality in assuming R k is R. So that is R, C22. So what are this? So C is a matrix which is C11, C12, C13, C22, C23, C33, everything, because it is symmetric I do not have to worry about the bottom part. But I can continue the C21, C31, C32. So I am going to compute all of these elements. You can see I have computed all of these elements like this. Look at this now, R plus this, R plus 2 terms, C21, C12. Now look at this, C21, 2 and 2, they are transposes of each other. We will talk about the symmetry of the resulting matrix in a minute, but I am trying to give you the exact expressions for the C's. So let me go back and remind you once more. I would like to be able to understand the presence of serial correlation, n observations. To make life simple, I assumed n is equal to 3. So I substituted n is equal to 3 in the expression for the forecast covariance, especially the random part of the forecast covariance. Using the random part of the covariance, I am simply computing expressions for these covariances. So C13, C31, C3, C32. You can really see I can compute this. From this you can readily see they are all related. So what if they so in the early methods based on 40 what did they not use? They did not use this term, sorry. They did not use this term. They did not use this term. So these are the new terms that comes into the picture, and it is these new terms we are interested in incorporating. Okay, I hope these expressions are clear. These expressions can be very explicitly evaluated by the closed form expression for the random part. So I have computed the matrix C. So let us go back now. I have computed the matrix C. Please understand, quadratic, in trying to consider quadratic forms, only the symmetric part of the C matters. So the symmetric part of C, so C is equal to C plus C transpose by 2. So we compute C as I have done and consider the symmetric part of C. So the new C is called the symmetric part of C. Now the correction term J3, okay, now look at this now. The correction term J3 in 13, let us go back. So 13, this is the new J function. Z inverse is to be used here, please understand. C inverse is used to be here. It is generally the case that I need to know the weight matrix. If I am going to consider the weighted least squares, I need to know the weight matrix. Weight matrix is C inverse. I have computed C. So in principle I can compute C inverse. Therefore the correct term J3, so J3 is the correct term in 13, is the quadratic form with the symmetric matrix C inverse, where C is the symmetric part of the computer. So what is this C? This is the computed C. This is the C that is used in the left hand side. C is the one that is used in 13. So you compute the deterministic part of the computed C, and that becomes the new C, whose C inverse is the one that is going to be used in the quadratic function. The inverse of the symmetric matrix of C is the one that is used in 13, and I would like to re-emphasize the fact which I have already mentioned. This matrix C depends on M, H and R. What is M? Model. What is H? Observation operator. What is R? Noise property. So you can readily see the serial covariance is a function of the model, the forward operator and the noise, all the three players in the game. So I have now completed one aspect of the estimation problem for the optimal G. This is using 4D VAR. So we talked about what they did, and we talked about what was wrong with it, and we also talked about what is the meaningful way to correct it. Now I am quickly going to provide a review of the second approach that was used in the post 90 era based on two-stage Kalman like scheme. It was introduced by a group of French atmospheric scientists, Vittard et al. 2003. This uses a Kalman filter like predictive part that combines it with a conventional nudging scheme. So you can readily see, so you can now see the following idea. If you knew some of the basic approaches to assimilation that we have covered in this class, you can hybridize these methods to be able to generate newer methods. So in this course we are not going to be talking about all possible methods of hybridization. We are going to be, we have described all the methods in their purest form, because before you can hybridize you need to understand what is the power of each of these techniques. Therefore, this being the first level course at the graduate level, we have emphasized all the basic tools which if well understood not only be applied directly, also can be used to devise newer schemes for data assimilation and other problems. That is the idea here. So this is an example of such hybridization. So what is the thing in here? The first step is the following. Let xk minus 1 be the state I know. I am using the model to create a forecast. The second step is I am going to do an analysis, which is forecast plus g times zk minus h of f. So what is this? This is the nudging part. Nudging part. So you make a forecast and then you create an analysis. The forecast comes from the model, the analysis comes from the nudging. The nudging uses a G. G plays the role of a Kalman filter, and they would like to be able to determine G using methods similar to the arguments in Kalman filter. You can see how the hybridization comes into play. So that is what I am going to quickly describe. So define dk, which is equal to zk minus h of xkf, which is the innovation, the new information that zk contains other than what the observation gives you. So d is the vector of such innovations. D is again a vector of size nm. Now I am going to concoct a jn x naught of g. Jn is called the nudging induced cost function. So that is equal to the transpose of this G transpose Pf inverse G dfn. So you can think of these three as part of the weight matrices. Pf is the forecast error covariance. So that is very similar to the one that comes in 4UR like scheme. Here, because of the way that G appears in equation 30, 31 is a very natural way to be able to consider a J function. So the model error covariance, so here look at this now, in here Pf is the model error covariance using Kalman filter. You may realize even if the model is linear, computing the forecast covariance involves two matrix multiplication. So computationally it is much more expensive than the 4UR based idea. Therefore they concocted several components for the overall minimization. One is the background term. What is background term? X naught. Until now we did not worry too much about X naught. So initially I may allow the error, but as the system picks up in time the error will reduce. That was the basic idea. Now they would like to be able to start with some background information for the model initial state itself. So that goes to show you the flexibility of how many such terms, if you knew, you can add to the objective function to be able to create a solution that takes care of several pieces of information that you may want to bring to bear on the problem. So J2 is essentially the sum of squared error criterion Please remember they used RK. We have now argued use of RK is not correct because the forecast errors are correlated. So in that sense the use of RK in 33 one essentially closes their eye to the presence of the serial correlation. So what is the best way to do it? You still need to be able to get an expression for the forecast error and need to be able to compute the serial correlation. Essentially you are trying to talk stochastic dynamic models with stochastic observation in the context of nudging. So when you are trying to do everything stochastic you need to call spade a spade, and using RK does not fit that paradigm. That is one of the observations that we have made. So you concoct a new cost function. Please understand until now we only considered a cost function which is a function of g. Now the cost function is a function of x naught and g. So it is a slightly extended formulation. So the j and g we have already seen, j to g we have already seen, jb x naught. So there is a penalty coming out of x naught, there is a penalty coming out of g, there is a penalty coming out of x naught and g. So our objective is to minimize not d3, I am sorry, is q3, sorry, minimize q3 using the adjoint method when the nudging model is used as a strong constraint. Now look at this now again. They concoct a Kalman-like scheme, but they want to be able to find the initial condition and the optimal g by methods similar to the adjoint method when using the adjoint the nudged model as a strong constraint. You can see the power of the 4D like principles where you can apply it repeatedly, whether it is estimating the initial state or parameters or anything else. So in this case g is a parameter, you can think of it for the nudged model. Since the forecast errors are correlated, we need to correct j to g. Please understand we need to be able to correct j to g. J to g is given by 33. So this is what we talked about. RK, the use of RK inverse. So all the other terms are kosher. The only term that does not fit the bill is because 33 relates to the total sum of squared errors, weighted sum of squared errors. The weighting is not appropriate, the weighting is incorrect. So we can again correct the weight function by appropriately computing the serial correlation. So the temporal covariance estimation is an important part of this. We only cited the need for computing this temporal correlation. We have not done this explicitly. I think it will be an interesting exercise for somebody to be able to take up this two-stage nudging scheme that involves 4D and the Kalman-like scheme and compute the serial correlated errors, and if you use that you should be able to find out what is a good scheme, what is a good method. So that could in my view a good starting point for probably a master's thesis, With this we have provided you a major all the major ideas that relates to the development of nudging schemes. We have given several exercises that are extensions of the discussions that we have had. This module follows a paper that we wrote in 2013, Lakshmi Varahan and Lewis, Nudging Method, a critical overview. This appeared as a chapter 2 in a book entitled Data Simulation for Atmospheric, Ocean and Hydrological Application. It is the second volume published by Springer Verlag in a series edited by Sangi Park and Yel Chu. And that paper contains a lot more information about basic nudging. We also alluded to the relation between observer theory as was developed by Leuenberger in early 1960s, 62, 63, 64 in the time framework. And in our paper, in our critical review, we have talked about the intrinsic relation between observer theory and the nudging theory to be able to see how observer theory can help to be able to design better nudging schemes. nudging schemes are general schemes which are very useful class of methods for forcing a model towards the observation by using the notion of this state feedback. So with that we conclude our discussion, an introductory discussion of nudging methods. Thank you.